All right, welcome. Now we're on part 2 of 2, and this time we're going to have the same givens, except now I want to know if we're going to sell apples and oranges by the ounce, what will be the mean and standard deviation of that situation? So I'm just going to put it over in this corner. Part C is going to be right here. Part C is going to be, suppose we sell apples for, these are expensive apples. We're going to sell them for $3 per ounce for the apples. The oranges are going to be $6 per ounce. So what will be the profit on a randomly selected, if we sell an apple and an orange, what is the expected, it's not profit, it's revenue. What's the expected revenue from the apple and the orange? So,
Selling one of each.
Selling one of each. So what's the expected? It's basically 3x plus 6y is the revenue model, correct? So what's the expected revenue and what is the standard deviation of 3x plus 6y? And so I'm going to press pause and go ahead and find those. Okay, so the camera is right back at you there. And so let's go over the answers to part C. Just going to plug in the power cable here. All right. So when you took 3 times 40 plus 6 times 34, are all of you in agreement that that is, what is it? $324? Do you all agree on that? Okay, so this one came up to be $324. And it's got to have units, 324. So this one's going to be the square root of, you've got to take the standard deviation 3.1 and multiply it by 3. 3 times 3.1 and square that thing. So it'll be 3 squared times 3.1 squared. 3 squared times 3.1 squared. And the other one will be 6 times 2.8. So the standard deviation gets multiplied by 6, and then you square it. So in this case, the 3 is getting squared and the 6 is getting squared. And when you typed that in, are you all getting $19.20? For, yeah, you didn't type it in? Okay. So can you show me how you typed it in on your calculator there, Garrett? Just so I can double check. Because it looks like a student typed it in and came up, yep, that's typed in correctly, $19.20. Okay, 2 more problems and then we're done. So take a picture if you want, erase the board, ready for the next problem. I'm going to pause the camera while I erase. Okay, in problem 3, we're going to look at the question of symmetric, skewed left, or skewed right. Now, if a sample size is big enough, then your binomial distributions will be symmetric. But what if you have a geometric distribution? Are geometric distributions always skewed left, always skewed right, always symmetric, or none of the above? Like, let's take the geometric distribution, say someone's a 99% field goal kicker, like, Cody Parkey was probably right up there. It's like almost fantastic. Except for when they block it, then it gets a double dunk. But he was fine otherwise. So what's that thing going to be? Symmetric, skewed left, or skewed right? Well, friends, it turns out that geometric distributions, probability, what's the probability that we have so many attempts till our first miss? They're always skewed right. So it's the number of attempts till the first miss. It could be that the first miss will never come, but these distributions are always skewed to the right. We never talk about a normal approximation of a geometric distribution. So if someone's asking about whether distributions are symmetric, skewed left, or skewed right, and they bring up geometric, you're always going to say it's what? Right. Always skewed right. The tail's on the right. Okay. Now, binomial distributions, like 100 comma NP 0.40. Okay. This thing's gonna start out binomial, so I mean it's gonna start out skewed, but if NP is greater than 10 and NQ is greater than 10, then it's going to be symmetric, because a normal model will be appropriate. The only time a normal model is appropriate is when it's symmetric. So that's how you'll know whether a binomial model is symmetric, skewed left or skewed right. It depends on NP greater than 10, NQ greater than 10. So that's all I wanted to do with example 3, was just discuss that symmetry issue. Now our final example, number 4, and then you'll be good to go. I mean, this is not everything that's going to be in the test, but these tend to be the tough ones. So suppose we have a random variable where it's x, probability of x equals x, and yeah, payoff times probability. So suppose we're playing a game in which you can win either $3, $5, or $10, and the probabilities of these are 0.4, 0.1, and 0.5. So I want you to find both the expected value of x and the standard deviation of x. It's a review problem, but a lot of people forget how to do it. You're allowed to use your calculator. You may begin, then we'll go over it. Let's just see where we are so far. So people did payoff times probability 5 times 0.1 plus 10 times, and they got 6.7. Okay, so store that in M on your calculator. Now, for those of you who are forgetting how to do the standard deviation, remember the formula for this. Before I actually give you the answer, the formula was, it's like x1 minus mu sub x, which is the expected value, squared times the probability of x1, plus probability of x1. Okay, plus x2 minus the mean of all of them squared times the probability. That this is actually, the technical notation is capital X equals x1. Multiply this by the probability that capital X equals x2, and keep going until you got them all. So that's just a reminder of what the probability formula is, or the standard deviation formula is for the standard deviation of a random variable. So I'm going to pause while you finish that up. Okay, I'm going to start talking through this one. Some of you are still typing it into your calculator. But the thing that I hope your calculator shows, if you type 6.7 for M, I hope that you're seeing 3 minus M quantity squared times 0.4 plus 5 minus M quantity squared times 0.1 plus 10, parentheses, 10 minus M quantity squared times 0.5. Hopefully that's how it looks on your calculator when you type it in. And it looks like everyone agrees that it's $3 at 0.35. Okay, so it's $3.35. So looks like if this were dollars, it'd be, the standard deviation would be 3.3. Well, it's actually okay to go to more than one. What was the other decimal? 351. Oh, it was 48. 3.348. Okay, yeah, that's appropriate for the standard deviation. Now, you gotta watch out, because sometimes people think that if there had been a 0 in here, like what if this had been 0.3 and this had been 0 and 0.2? What if this had been the original distribution of the random variable x? Then this column doesn't matter when it comes to expected value, because 0 times 0.2 is 0, it doesn't matter. However, it does matter for the standard deviation, because 10 minus M squared times 0.3 would be the third term. 0 minus M is not 0. 0 minus M would be, I mean, this will be a different number here because I changed it. So make sure that when you're calculating the standard deviation, you get all of the, even the 0 column, if there is a 0 in there. Okay, so that concludes the review session. Come either Thursday before school or Thursday after school to take the Makeup Unit 7 test. Thanks for coming. Have a good night.